Okay, so this video is going to be about the Diels-Alder reaction and some of the key features that you'll need to know about this reaction. So firstly, the components of a Diels-Alder reaction are a diene, a dienophile, and the product is a cyclohexene. So the diene, that's fairly obvious where we get the name for that. The dienophile, it may seem like a strange way of referring to it when it's normally just an alkene, but I guess sometimes the dienophile may be some other kind of double bonded species, such as a carbonyl group. And so a dienophile is the more general term. And the product of a Diels-Alder reaction, because we're normally going to be using an alkene, is a cyclohexene. So a 6-membered ring with a double bond in it. The second key feature is that the Diels-Alder reaction is reversible. And so normally we show this just in the one direction. Normally we use Diels-Alder reactions constructively to build up bigger molecules from simpler components. But at high temperatures, the Diels-Alder reaction actually quite often favors the retro process or the reverse process. So we would call this a retro Diels-Alder. So at high temperatures, this becomes favorable in the reverse direction because of entropic factors. So we would call this entropically favored. So at high temperatures, there's a couple of reasons why it's entropically favored. One of which is that we take a single component and we generate 2 molecules from that, and that's an entropically favored thing. But also the transition state involves a high degree of organization, and so entropy is sort of working against us in that manner. The third key feature is that electron-withdrawing groups on the dienophile dramatically enhance the rate of the reaction. So if we have one electron-withdrawing group, we get a much faster reaction. If we have 2, it becomes even more greatly favored or more kinetically favored. So when we talk about electron-withdrawing groups, we're quite often talking about groups that are pi electron-withdrawing. So here I've got a cyano group. If we draw out that molecule in full, we've got a triple bond between a carbon and a nitrogen, and indeed that is inductively electron withdrawing. So through the sigma bond it's pulling electrons away because the nitrogen is withdrawing electrons from the carbon, and then that's having a flow-on effect to the alkene. But probably more importantly is the pi effect, or the resonance effect. So this structure that we've drawn here, we can draw resonance. We can draw a curly arrow showing a resonance form. We push electrons toward that bond there, and then we push out electrons onto the nitrogen, and we can draw another resonance form of this particular compound. Oops, we don't have that second bond there, that pi bond. We now have this bond here, a carbon, and a double bond to that nitrogen. And we're now going to have a full negative charge on that nitrogen and a full positive charge on that carbon. And that's showing why, this is one way of showing why that alkene is relatively electron deficient. And so this resonance structure contributes to the overall structure of this alkene, giving it a sort of partial positive charge, and therefore making it more reactive. A more sort of precise way of talking about this is that the electron withdrawing group lowers the LUMO of this species, and that brings the LUMO of this dienophile closer to the HOMO of the diene. And that makes those 2 orbitals overlap more effectively, and therefore lowers the energy of the transition state for this reaction. Okay, our fourth key feature is that the alkene geometry, if there is alkene geometry, so normally we'll need 2 substituents on the alkene for that, translates into product stereochemistry. So if I take one diene here, in this case I've got butadiene, and I take one geometry of an alkene, so in this case we've got the E alkene geometry, that translates into a trans geometry of the product cyclohexene. However, if I take the opposite geometry of the dienophile, so in this case now we've got the Z dienophile, that then translates into the, sorry, not the Z, the cis stereochemistry of the product, cyclohexene. And so we would call this a stereospecific reaction, or more explicitly a diastereospecific reaction, because one geometry of an alkene gives one diastereomer of the product, whereas the other geometry of the alkene gives the other diastereomer of the product. Our fifth key feature is that only the s-cis conformation of the diene is reactive. So S in this case stands for a single bond. So we're looking at the conformation around that single bond between the two alkenes. So if we have a diene in which we can't get to an s-cis conformation, we do not get any reaction of that diene. So we get no reaction in this particular example given here. And this is quite often a little bit confusing, and it's easier seen with models. So if I get a model of this molecule here, so we've got the cyclohexene with an external alkene. I'll turn around towards the camera there. So there we have the HOMO of the diene, and that has to interact with the LUMO of the dienophile. So hopefully this is in the camera, in the view there. So we have to get efficient orbital overlap between this orbital here of the alkene, the dienophile, and the diene, but also this lobe over here of the diene HOMO with the LUMO of the dienophile. And we can't get efficient overlap of those two at the same time in this S-trans conformation. And because it's a cyclic system, we can't prise that apart and get those two closer together through an s-cis conformation. And so this reaction does not occur. Okay, so I've remade the diene model into an acyclic molecule. So this is just butadiene. And I've put it into the s-cis conformation. And now hopefully you can see that it's much easier to get efficient orbital overlap between the LUMO of the dienophile with the HOMO of the diene. So we can get efficient orbital overlap like that. And so the Diels-Alder reaction takes place because we get this s-cis conformation of the diene. Okay, and our final key feature here is that where we have bicyclo compounds produced, the so-called Endo product is preferred. So I've chosen deliberately the diene to be cyclopentadiene because this is very often used. You'll see it in whatever your textbook is. So this cyclopentadiene is always in the s-cis conformation. The cyclic system is holding in that conformation. And so cyclopentadiene is one of the more reactive dienes. And here we have a very reactive dienophile. It has two electron-withdrawing groups. These two carbonyl groups are making the LUMO of this dienophile much lower. And so there's very efficient orbital overlap between these two, and the cyclopentadiene is always in the s-cis conformation. So this is one of the most commonly sort of shown examples of Diels-Alder reactions because it's incredibly fast Diels-Alder reaction. So if you react these two together, we get two different products, and these can be labelled as either the Endo or the Exo products. And the Endo refers to whether the leftover alkene within the product, or the larger bridge, is on the same face of the molecule, on the same side as the rest of this maleic anhydride unit. These carbonyl groups are on the same side as that alkene. Whereas in the exo compound, they're on opposite sides. So exo is opposite, endo is same. And the endo is normally preferred in Diels-Alder reactions. So we can say that that is favoured or desired or preferred, and this is disfavoured. Or I guess when we do the experiment, what we might say is that the endo product is the major product and the exo is the minor. Okay, so there's 6 key features of the Diels-Alder reaction. There's one that's still remaining, and that is that there's regioselectivity possible in some Diels-Alder reactions. But that's quite a weighty topic, and that'll be the subject of an entire video just to itself. Okay, so I hope that helps explain some of the key features of the Diels-Alder reaction.